This tutorial is a set of videos outlining a number of steps to build a full Spring Boot application featuring a Kotlin service backend, a Java client, and a JavaFX user interface. The first step in the tutorial is to create a Kotlin Spring Boot application which serves as the backend of the application. Let's create a new project for our Spring Boot service. Since we're using Spring Boot, we'll select the Spring Initializer option on the left of the New Project window. We can select which SDK to use. We'll use Java 13 for this project. We enter a group name for our project and an artifact name. We can build this project with Maven or Gradle, and there are various options here. We're going to create a Maven project which will generate the pom.xml and Maven wrapper files that we need. For this service, we're going to choose Kotlin as our language. We'll select Java 11 here, as this is the most recent long-term support version for Java, but for the purposes of this project it makes no difference. The name is automatically populated from the artifact name, we don't need to change this. We should add a useful description for the project, and we can optionally change the top-level package too. We can choose which version of Spring Boot to use, including the most recent production-ready version, or snapshot versions to try out. We're going to use 2.2.0 RC1 for this tutorial, because later we'll be using features that are only available in the release candidate. We can also search for and select which Spring Boot starters we want to use. This will be a reactive REST service, so we want reactive web. We'll use the defaults for project name and location. IntelliJ will use Spring Initializer to create the project and then import it correctly into the IDE. Let's enable auto import on Maven, so if we make any changes to the pom.xml file, the project will automatically be refreshed and rebuilt. You can see that IntelliJ automatically recognizes this as a Maven project and opens the Maven window. In the project window, we see the structure of the project that has been created, including a Kotlin directory and the standard default application class that Spring Boot creates. IntelliJ Ultimate has full support for Spring applications, which includes gutter icons, making it easier to identify and navigate between Spring elements like Spring Beans. If we take a quick look at the generated pom.xml file, we see not only the selected Spring Boot starters and Kotlin dependencies, we can also see the Spring compiler plugin in the Kotlin Maven plugin. This makes it a bit simpler to work with Spring in Kotlin. Let's go back to the application class and run it using the shortcut Ctrl-Shift-F10 for Windows or Linux, or Ctrl-Shift-R for Mac, just to see that everything works together correctly. We can see it started successfully with Netty running on port 8080. Let's stop it with Ctrl-F2 or Command F2 for the Mac. Now we know it all works, we can get started on our own functionality. Let's create a class for our REST controller. We'll put it in the same Kotlin file to keep things simple for now. We need to annotate this as a REST controller. We can use the Fun1 live template to automatically create a Kotlin function that takes a single parameter. We'll call this method prices, and it takes the symbol of the stock we want to get the prices for. This method will return a flux, which will be a constant stream of prices. This is where the reactive part comes in. The flux will emit stock prices. I use Alt and Enter to get IntelliJ to automatically fix up my code. And then we need to create this new stock price class, which will represent all the data we need to know about the price of a stock. Again, we'll keep this inside the same file to make it easier to see. We're going to create this as a Kotlin data class. This is a compact way to declare a class with properties. In Java, this would have getters and maybe setters, and equals, hashcode, and toString methods. But in Kotlin, we simply declare what we want in the constructor parameters. We want a symbol for the stock, which is a string, a price, which is a double, and the time associated with that price. Here we're using Java 8's java.time.localDateTime. Now we're going to define what the prices method returns. This method is going to create a flux which emits one randomly generated price every second. We can do this with an interval with a duration of 1 second. Then we can use map to create a new stock price for each of these seconds. Note that in Kotlin we don't need the new keyword. The stock price needs the symbol, a price, which for the purposes of this tutorial will be randomly generated, and a time, which will be now. Let's import this now method to make the code a bit shorter. Now we'll create the random stock price function. IntelliJ knows this needs to return a double because of the stock price constructor. One way to create an arbitrary double is using thread_local_random and the next double method. Let's generate a number between 0 and 100. The last thing we need to do to make sure this compiles is to return this flux. Since we want to be able to access this method via an HTTP GET call, we need to add the GET mapping annotation to it. We'll give it a path. I tend to define this as a string parameter and then get IntelliJ to turn it into an array. We need to define what the response to this method looks like. We're going to use text event stream value. So this is a server-sent events streaming endpoint. Again, I'll use IntelliJ to wrap this in an array. One final warning from IntelliJ that needs fixing up. The IDE has detected that we're using a path variable, but we haven't defined it in the method parameters. One way to fix this is to get IntelliJ to create the path variable and remove the parameter we created earlier. If we run the application, we can see it starts up correctly. If we open up a web browser and navigate to the path we defined, we'll see the events tick once a second and see the stock price represented as a JSON string. We've created a simple Kotlin Spring Boot application that uses reactive streams to emit a randomly generated stock price once a second. In the rest of this tutorial, we'll show how to connect to the server to retrieve prices and how to create a chart that shows the price updates in real time. In this next section, we'll see how to create a reactive Spring Java client that connects to our REST service streaming prices once a second. We're going to create a new project for this client, since we want to keep the client and server code completely separate as they should run completely independently. This project will have multiple modules in, so we'll start by creating an empty project. Let's call the project Stock Client. By default, IntelliJ shows the modules section of the project structure dialog when a new empty project is created. We'll add a new module here. This will be a Spring Boot module, so we choose Spring Initializer on the left. We'll use Java 13 for our SDK. We enter the group and artifact details here. Let's call this module Stock Client. We'll enter a useful description for the module so it's clear what the purpose of this code is. We'll keep the defaults of creating a Maven project with Java as the language, but we'll pick Java 11 as the version, as this is the current long-term support version. We can optionally change the default package structure if we wish. We'll pick Spring Boot 2.2.0 RC1 because we'll need some features from this version in later videos of this tutorial. We need to select the Spring Reactive Web Starter, and we're going to select Lombok too. The defaults for module name and location are fine, so we'll keep them as they are. IntelliJ gets the project from Spring Initializer and sets up the IDE appropriately. For example, it's recognized the project as a Maven project. In the standard project structure, we can see the stock client application that Spring Initializer has created for us. We don't need this for this module, as this module is going to be a library that other applications use. It's not going to be an application in its own right. Instead, let's create a class Web Client Stock Client. This is going to use Spring's web client to connect to the stock prices service. One way to drive out the requirements for our client and to see if it actually works is to develop it in a test-driven way. Using Ctrl-Shift-T or Command-Shift-T, we can navigate to the test for a class. We don't have one yet for this class, so let's create one. We're going to use JUnit 5, but IntelliJ IDEA offers a range of testing frameworks to choose from. This is actually going to be an end-to-end test, not a unit test, so let's rename the class using Shift F6 so that it more accurately represents the type of test. Let's generate a test method using Alt and Insert or Command-N. This is not going to be a perfect example of test-driven development, as we're going to create just a single test which looks at only the best case, sometimes called the happy path. We need to create an instance of our web client stock client in order to test it. Let's put this into a variable so we can use it. One of the things we can do with test-driven development is to code against the API we want, instead of testing something we've already created. Let's say we want our client to have a method called prices4, which takes some string that represents the symbol of the stock we want the prices for. We can use Alt and Enter to get IntelliJ IDEA to create this method on web client stock client with the expected signature. We actually want this method to return a flux of stock price objects. The simplest way to create a method that compiles so we can run our test against it is to get this method to return an empty flux. We will build up the real logic later. Now we need to create our stock price class. It's easiest to get IntelliJ IDEA to create the class using Alt and Enter. We can pick which package we want it to go into. Let's just put it into the same package. Here we're going to use Lombok. Using Lombok's data annotation, we can create a data class similar to our Kotlin data class from the first video of this tutorial. By annotating this with data, we only need to define the properties of this class using fields. The getters, setters, equals, hashcode and toString methods are all provided by Lombok. Use the Lombok IntelliJ IDEA plugin to get code completion and other useful features when working with Lombok. This stock price will have a string symbol, a double price, and a local date time, the same as the Kotlin class on the service side. We'll add an all-args constructor and a no-args constructor via Lombok. These are needed for our code and for JSON serialization. If we go back to our client, we can see everything is compiling. Let's navigate back to our test and finish it off. Now we have a flux of prices, we need to check this meets our expectations. If this was connected to a real working service, we'd expect the prices flux not to be null. We'd also expect that if we take 5 items from the flux, that there are actually some items there. We have to use block in this case to wait for our prices. When we run this test, we see that it fails. It fails because the flux has 0 elements in it, because that's what we hard-coded into the client. Let's go back to the client and make the changes needed to connect it to the real service. First, we want to use a web client to connect to the service. We'll create this as a field and add a constructor parameter so that Spring automatically wires this in for us. Now we use the web client to make a GET request. We give it the URI of our service. We know what this was as we put the URI into the browser to test the service when we created it back in the first video. We need to use the given symbol in the URI. Then we need to call retrieve. We need to say how to turn the response of this call into a flux of some type. So we use body to flux and give it our data class stock price. These are the very basic requirements to get a reactive stream from a GET call. But we can also define things like the retry and backoff strategy. Remember that understanding the flow of data from publisher to consumer is an important part of creating a successful reactive application. We can also define what to do when specific exceptions are thrown. As an example, we can say that when we see an I/O exception, we want to log it. We'll use the log4j2 annotation from Lombok to give us access to the log, and then log an error. This is not the most robust way to handle errors. This simply shows that we can consider exceptions as a first-class concern in our reactive streams. Going back to our test, we see we now need to give our client a web client. Let's create this as a field in the test. Using smart completion, which is Control-Shift-Space, IntelliJ IDEA will even suggest the full call to the builder that can create a web client instance. If we needed to, we could use the builder to configure our web client even further, but in our case we can use the default settings. We want to run our integration test to see if our changes work, but first we need to make sure the service is up and running, otherwise we won't be able to connect to it. We need to go back to the stock service application we created in the first video and start this. Once this is running, we can run the client test. This time the test goes green. And if we look at the output, we can see we're decoding stock price objects with the symbol that we used in the test, random prices, and a time. This is not the most thorough test, so let's add a bit more detail to our assertions to make sure the client really is doing what we expect. Let's change the assertion to require 5 prices when we take 5 prices, and let's make sure that the symbol of one of the stock prices is what we expect. Testing reactive applications is a skill in its own right, and there are much better ways to do it than we've shown in this simple example. However, we have successfully used an integration test to drive the API and functionality of our stock prices client. This client connects to an endpoint that emits server-sent events and returns a flux of stock price objects that could be consumed by another service. In this section, we'll create a Spring Boot JavaFX application so that JavaFX can take advantage of Spring features like dependency injection. We're going to reuse the client project from the previous step and add a new module to it. But we could create this as a new project rather than a new module. The steps would be very similar. Let's create a new module for this project. This is a Spring Boot application, so we select Spring Initializer from the options on the left. We've selected Java 13 as our JDK, but we're not using any recent features, so feel free to use any version from 8 onwards. We enter the group, and we'll call the artifact Stock UI. We keep the defaults of a Maven project with Java and jar packaging, but select Java 11. Let's enter a helpful description for the module. This is our third module, so it helps us to keep clear in our mind what each module is responsible for. We can optionally change the default package. Here, we can select any of the Spring Boot starters we need, but for this module we don't actually need anything. We can keep the default module name and location. IntelliJ IDEA downloads the created project from Spring Initializer and sets up the IDE correctly. If we're given the option to show the run configurations in services, we can select this. The services window is a slightly nicer and more useful way to see our running services and can help us manage microservice applications. As usual, Spring Boot has generated a default application class for us. We will need to change this in order to launch a JavaFX application. Since this is a JavaFX application and not a web application, we can set the Spring Web Application type to none. Now let's create our JavaFX application class. We'll call it Chart Application, since later in this tutorial this application will be displaying a line chart that updates itself with stock prices in real time. Since this is our JavaFX application, it needs to extend application. This is not currently on the class path since we haven't declared it in our dependencies. Pressing Alt and Enter on the red application text gives us the option to add Maven dependency. We want to add OpenJFX JavaFX graphics as a dependency. Here we're using an early access version of 13. If we go to our pom.xml file, we can see IntelliJ IDEA has added this dependency to the file, and in the background downloaded the required jar files. We can now import JavaFX application. Application is an abstract class, so we need to implement some methods. We can get IntelliJ IDEA to implement these methods by pressing Alt and Enter, selecting Implement Methods, and choosing the methods to implement. Now we have a JavaFX application, we need to launch it from the Spring Boot application. Instead of using Spring Application to run the application, we'll use the JavaFX application class. and call launch with a class that is our JavaFX class and the application arguments. The reason we need two separate application classes for our application is because of the way JavaFX uses Java modules. It's beyond the scope of this video to go into the details. Let's go back to our JavaFX application class, chart application. We want to be able to make use of Spring functionality, like having access to the application context. Let's create a field for application context. This will be a configurable application context. We will look at how to create this in a minute. Our start method, which is a standard JavaFX method, is called with a stage object when the stage is ready to be used. The stage is what we will draw on when we have something to show. We can use the Spring pattern of publishing events via the application context to signal when this stage is ready. We'll give the event to the stage so that anything listening to that event has access to it. This primary stage parameter was created by IntelliJ. Let's rename it to stage to make it a little shorter and easier to read. Now we need to create our stage ready event. Let's create it as an inner class in chart application for simplicity. IntelliJ creates the constructor that takes stage as a parameter. We'll pass this into the super constructor. We can make this inner class static. We don't want the event to be private as other classes will be listening for this event. There are some other useful methods in application that we can override and make use of. Let's override init. This is where we need to initialize our application context. We'll use the Spring application builder and give it our Spring Boot application class, which was stock UI application, not this chart application. We call run to get the application context. Since we have an init method, we should probably have some sort of teardown or cleanup too. Let's override application's stop method. Here, we can close our application context and exit our JavaFX application. Finally, just a bit of cleanup in this class. IntelliJ is telling us these exceptions are not thrown, so we can just go ahead and remove them. Now we have our Spring Boot application class, which launches our JavaFX application. We need something which is going to listen to the stage ready event that we created. Let's create a stage initializer class, which will set up our JavaFX stage when it's ready. This class needs to implement application listener, listening for our stage ready event. This line is a bit long, so let's import the stage ready event to make the code a bit shorter. We need to implement the methods on this interface. Let's get IntelliJ to do this for us. The IDE has created an onApplicationEvent method for us, which takes the stage ready event. Let's also annotate this class with component, so that Spring can do dependency injection and so on in here. Let's go back to the onApplicationEvent method. What we want is to get the JavaFX stage from this event so we can do something with the stage. The getStage method doesn't exist yet, so we can get IntelliJ to create this for us. We want this to return a JavaFX stage. The superclass actually has a method that does what we want, getSource. This returns an object, so let's cast this to stage. We actually know the source is a stage because when we passed our stage constructor parameter into the super constructor, this became the source. Back in the stage initializer class, we can assign the result of this method call to a stage local variable. This stage is ready for us to set up our user interface. We can now run our stock UI application and see it successfully start up as a Spring Boot application. It does also launch a Java process which would show a UI if we'd created one. We can see we've successfully created a JavaFX application which is launched and managed with Spring and allows us to use the convenient features of any Spring application. In this section, we're going to continue working with our Spring JavaFX application and get an empty line chart. We'll populate it with data later in the tutorial. Let's open the stock client project that we created back in video 2 and go back to the stock UI module that we created in video 3. This module had 2 application classes and a stage initializer. We're going to update the stage initializer to display the UI for this application. The stage will need a scene. This is the container we're going to put the UI elements into. The scene needs a parent, which we'll create in a minute. And we can set the width and height of the display here. Let's use 800 by 600. Let's create this parent as a local variable. IntelliJ IDEA works out that this needs to be of type parent. I'm going to move this to the top of the method so all the stage functionality is together in the method. While we're thinking about the stage, let's call show so we don't forget to display it. Now we need to work out where this parent is going to come from. We're going to use fxml to define what elements are on the user interface. Declaring the view elements in fxml gives a nice clean separation between the view and the model and controller if we're following an MVC pattern. We haven't declared a dependency on fxml classes yet, so let's add a Maven dependency. We need to add a dependency on JavaFX fxml. IntelliJ IDEA will add the relevant dependency to the pom.xml and download the required jar files. Now we can import the fxml loader class. The fxml loader needs to know the location of the fxml file. We'll say this can be found in a chart resource. We'll create this as a field in the stage initializer. It's going to be a Spring resource. We can use the value annotation to tell Spring where to find the file. Let's say it's on the class path and it's a file called chart.fxml. The fxml loader needs a URL, not a resource, so we'll call getURL on the chart resource field. Let's assign this to a local variable so we can use it later. GetURL throws an exception, so we'll surround the call with a try-catch block. In the catch section, we'll throw a new runtime exception for the purposes of keeping the tutorial simple, but this is not a useful way to deal with exceptions in production code. If the exception is thrown, none of the rest of the code can be run, so we'll move the catch block down underneath the rest of the method body. Now we can finally initialize our parent by calling fxmlloader.load. We need to create our fxml file. Let's go to the resources directory and create a new fxml file, chart. IntelliJ IDEA creates a basic fxml file for us, and we can fill in the details we need. A view usually needs a controller. We'll declare ours is called chart controller. IntelliJ IDEA has code generation even inside the fxml file, so we can create this missing controller class from inside the fxml file. This has been created in the default package. Let's move it into the same package as all the other classes. A move like this always uses the refactoring capabilities of IntelliJ IDEA, so files are moved safely. If we go back to chart.fxml, we can see the path to the controller has been updated with the full package name. We don't need the default height and width here. We'll set this in a different component. We're also not going to use the anchor pane. We'll change this to a VBox. We can use optimize imports to remove all the unnecessary imports from the fxml file. Let's see what happens when we run this application by going back to the Spring Boot application class and running it using Ctrl-Shift-F10 for Windows or Ctrl-Shift and R for the Mac. The application runs in the Services window because it's a Spring Boot application, and a Java window pops up at the dimensions we set in the stage. There's nothing in there yet as we haven't put anything into the view. Let's make a small change to see that we can control what is displayed in the window. We'll go back to Stage Initializer and set a title for the view. Let's create a field for application title and get IntelliJ IDEA to create a constructor with the appropriate parameters to initialize this field. We can use Spring to populate the value of this title. When we rerun the application, we can see JavaFX uses this new title in the title bar. Hard coding string values is not good practice for a number of reasons, so let's get this title from somewhere else. In application.properties, we can add a new property and call it something like spring.application.ui.title. Then we can set the value for this title. Back in Stage Initializer, we can use Spring Expression Language to say that we want to use this property for the title of our application. Now when we run the application, we see this value from Application Properties used as the title of the window. There's one last thing we need to do to make the most of Spring in this JavaFX application, and that's to be able to use the beans from the application context in the JavaFX wiring. FXML Loader has a method setControllerFactory, which we can use to say where we want to get our JavaFX controllers from. We want to get these from the application context, so first we need to create a field for application context. We can add a new constructor parameter for this field so that it's auto-wired in. Once this is set up, we can call getBean on application context to provide the controllers that JavaFX needs. All our wiring is complete, so let's finally create our line chart. In chart.fxml, we'll declare we want a line chart. A line chart has an x-axis, which for our purposes is going to be a category axis. In other words, it's going to have a series of strings as values. This is our time axis. The y-axis, on the other hand, is going to be a number axis. This axis is for the stock price. Let's set the height of the chart to 600, the maximum height for our application. We also need to give it an FX ID, which is the ID of the field in the chart controller that will contain the reference to this line chart. Let's call it chart. IntelliJ correctly identifies there's no field called chart in the controller class, so let's get it to create the field for us. We set up this line chart as a chart with a string x-axis and a number, or in our case, double y-axis. We can use the FXML annotation to show this field is populated from an FXML file. Let's also annotate the class as a component. Now, when we run the application, we see the outline of a line chart shown in our window, with numbers for our price axis and time on the x-axis. We have successfully created a JavaFX application that is integrated into Spring Boot that uses FXML to declare what should be in the view. In this section, we're going to set up auto-configuration for Spring Beans so that we can use beans defined in our stock client module in the stock UI module. Let's go to the chart controller class we created in the last video. This class is going to be responsible for updating the data we display on the line chart. Remember that this project is made up of two modules, the stock UI module that contains the JavaFX application, and the stock client module that contains the code that connects to the Kotlin stock price service. Our chart controller needs to use the web client stock client from video 2. It will use this to connect to the stock prices service. This stock UI module doesn't have a dependency on the stock client module, so we'll get IntelliJ to add this. You can see it does this by adding the dependency in the maven pom.xml file, so this dependency is managed by the build file, not by the IDE. Now we can import the web client stock client class. Let's add a constructor parameter so it gets wired in. IntelliJ helps us here as it tells us there are no beans of this type available. Let's fix this. Back in the stock client module, we need to create a new Java class. Let's call it client configuration and add the configuration annotation. Here we'll define our beans. We want a web client stock client bean. To create one of these, we need to pass in the web client. We can get IntelliJ to pass in a parameter for this, but we still need to define where this comes from. One way to do this is to define another bean, which is a web client. We can use the web client builder to create a new instance. We can also annotate this method with conditional on missing bean, which means this method will only be used to create the bean if a web client bean doesn't already exist. We're using this here because it's possible that something else that uses this code might also create a web client. Back in the stock UI module, we still can't see this bean. That's because it was defined in a different module, and this module can't see the beans defined there. Let's share the stock client context with the stock UI module. One way to do this is to create a meta-inf directory in stock client, and inside this, create a spring.factories file. Inside this, we want to set the property Enable Auto Configuration and define a configuration file. This will give other modules that use this module access to the beans in our client configuration file. Now, when we go back to our chart controller class, it knows where to find the web client stock client bean. In this section, we're going to get the JavaFX line chart to show the real-time prices coming from our Kotlin Spring Boot service. First, we need to create an initialize method, which is called once any fxml fields have been populated. This initialize method will set up where the chart data is going to come from. We need to set the chart data from something. The chart data is a list of series, as the chart could display more than one series of data. Let's create a local variable for this list. We want to add a series to this list. This series object is initialized with a list of the data points that make up the series, which we'll declare as a field in this class. Our data is a pair of string and double. We'll initialize this to an empty list for now, as our chart doesn't have any data to display when it starts. We need to get the data for our chart from somewhere. This is what we added the web client stock client for. We ask the client for prices for a given stock symbol. Let's hardcode a value in here for now. Given this is reactive programming, what we need to do now is to subscribe to the flux that is returned from this call. The simplest thing to do here is to subscribe the chart controller itself. At the moment, the chart controller isn't the right type for this. One approach is to make this class implement java.util.function.consumer and have it consume stock prices. We can get IntelliJ IDEA to implement the methods required to fulfill this interface. Now let's think about what we need to do with a stock price when we receive one. We need to add the right values from the stock price to the chart's series data. We want time on the x-axis. Let's use the second value as this is the simplest way to have the prices tick along. This is an int value, so we should use string.valueOf to make it fit our expected chart type. The y value is going to be the price of the stock. This looks fine, but there's another thing to consider with this programming model. Changing the series data will be reflected by an update in the user interface, which will be drawn by the UI thread. This accept method is running on a different thread, listening to events from the backend service. So we need to tell the UI thread to run this piece of code when it gets a chance. We do this by using the platform.runLater method, passing in a lambda expression of the code to run on the UI thread. Let's see what it looks like now. First, we need to make sure our backend Kotlin Spring Boot service is running. It needs to be emitting prices for our chart to listen to. Once this is running, we can go back to our UI module and run our JavaFX application. We can see that with these very few lines of code, we've created a JavaFX line chart that uses Reactor to listen to a Spring Boot service and update itself in real time. Let's change this label to something more useful. We'll extract the symbol into a local variable. We want to use it in more than one place. We can give the series a label, so let's use the symbol name for that. Now, when we rerun the application, we see the symbol's name here on the label for the series. This code is a little bit unwieldy with all the type information, so we can import series itself to remove the unnecessary XY chart prefix. We can add a static import for observable array list, so we don't need to repeat FX collections everywhere. We can add an import for valueOf to make this line a little shorter, and we can import the data class to remove another repetition of XY chart. These refactorings shouldn't have changed the behavior of the code, so when we rerun, we'll see everything working the same way as before. So there we have it, a JavaFX application that uses Spring's web client to connect to a Spring Boot service, subscribes to the reactive stream of prices, and draws the prices on a line chart in real time. In this section, we're going to update the chart so that it subscribes multiple times and can show multiple sets of prices on the same chart. The chart controller, which manages how the data gets to the view, contains a call that subscribes the chart controller itself to the client that listens to the price service. We need to change this so we can have more than one subscriber. Let's create a new type, a price subscriber, which manages everything to do with consuming prices from the client. We'll create this as an inner class. We know from the last lesson that this accept method is the one that deals with the prices. So let's move this into the price subscriber and make a small change to get the price subscriber to compile. We want the price subscriber to manage the series data, as this is the collection that gets updated by the accept method. We also need the price subscriber to know the symbol. Each subscriber is responsible for managing a single stock. We'll get IntelliJ to create the appropriate constructor and to create a field for the symbol parameter. Since each stock also corresponds to a single series in the chart, we can also move the creation of the series into the price subscriber. Let's move the series into a field so we can use it elsewhere in the class. We can make all these fields final since we're not going to change them anywhere once they're initialized. We need to add a getter for series because the chart controller will need to get this series to add it to the chart. Let's extract the price subscriber into a local variable. We're going to need to use this elsewhere in the method. To declare this as final, we can hold down Alt and press the F key. Let's move this price subscriber near the top of the method. Now we can get the series from it to add it to the chart. The chart controller still doesn't compile because we said it still implements the consumer interface, which it doesn't anymore. So we need to delete this. If we rerun the application, the chart should run the same way it did before, assuming we still have the backend service running as well, since we haven't changed the behavior, just refactored the subscription code. Now we want to add our second subscriber. Let's rename our symbol to symbol 1, since we're going to have another one of these. And let's also rename our price subscriber as well. We can duplicate these lines and make them work for a second symbol. The second symbol and price subscriber are needed for a second subscription to the client that retrieves prices. We also need to add our second series to the chart to display the second set of prices. Let's rerun the application to see if this has worked. Now we can see two different series on the chart tracking the prices for two different stocks. Now we have the application working the way we want, we can refactor the code if we wish. For example, we might want all the code that sets up the subscription for each symbol in the same section of the method, so we could move the call to subscribe to the top, near where we create the subscriber. We can clean up any warnings, so here we can make the inner class static as suggested. And although we thought we might need symbol as a field, it turns out we don't need it elsewhere in the class, so we can convert it to a local variable. IntelliJ automatically inlines this since it's only used in the call to the series constructor. So now we have a JavaFX application that subscribes to more than one price from our Spring Boot service and displays each set of price data in real time in multiple series on a line chart. In this section, we're going to create a Kotlin service that publishes price data over the RSocket protocol. Our existing service is a Kotlin Spring Boot application with a REST controller. We're going to create a similar class, which is an RSocket controller. It needs to be annotated as a Spring controller. Let's create a new Kotlin function that takes a single argument. We'll call it prices, the same as the REST controller function. This takes a symbol, which is a string. We want this function to return a flux of stock prices, as it's going to produce a stream of prices. In fact, this method is going to look a lot like the prices method in the REST controller, since it's actually going to do the same thing. The only difference is it's going to publish the prices in a different way. To reduce duplication, let's introduce a price service that contains the shared logic. Let's get IntelliJ to pass this in as a constructor parameter. In the change signature pop-up, we can define this as a new type, price service. We haven't created the service yet, so let's get IntelliJ to create the class inside this file for simplicity. We'll annotate it with service. Let's call a function on the service called generatePrices. We know we want to pass in a symbol and return a flux of stock price objects. IntelliJ can figure out from our code how to generate a function with the correct signature. We know what we want inside this function. This is the functionality that's going to be shared between the REST controller and the RSocket controller, which is currently in the prices function of REST controller. Let's copy this from prices into the new generatePrices method. We also need the random stock price method from the REST controller. Now everything here is compiling, we can remove our duplicated code. We can introduce the price service to the REST controller as well. And we can call the generatePrices function to get the prices for the REST controller. Now we can safely remove the random stock price function since it's not being used because we copied it into the service. The prices functions on both the REST controller and the RSocket controller are now simply calling the price service, so all the common code is in one place. Kotlin allows us to simplify this code even further. We can convert this to a function with an expression body, which also allows us to remove the declared return type if we wish. Because this function is a simple delegation, this might be a more useful and certainly shorter way to write it. The REST controller function is annotated with getMapping, which sets up the URL for clients to connect to consume this stream of prices. We need to do something similar for the RSocket controller function. For the RSocket prices function, we need to add a message mapping annotation. We haven't added the dependencies we need yet, so let's go ahead and add the dependency to our pom.xml file. Notice that IntelliJ can help us with code completion. Once we've added Spring Boot Starter RSocket to the POM file, now when we go back to our application file, we can add an import for message mapping. We need to give it a string root so that clients can connect to this. If we start the application now, we can see which servers have been started. In this case, we only have Netty on port 8080. We want an RSocket server as well. Let's go to Application Properties and define an RSocket server port. Let's use port 7000. Simply defining the port here is enough to get Spring Boot to start an RSocket server for us. So when we restart the application, we can see a Netty RSocket server started on port 7000. Now we have a prices service started on port 7000 ready for a client to connect to it to receive stock prices via RSocket. In this section, we'll see how to create a Java client that connects to our RSocket price service. As with the web client stock client, we're going to drive the RSocket client with an integration test. The test looks almost identical to the web client stock client integration test, so let's copy this test and rename it to RSocket stock client integration test. We need to change this to work with an RSocket client. First, let's declare an RSocket stock client variable. RSocket stock client doesn't exist yet, so let's create it. For now, we'll leave it as an empty class so our test compiles. We'll come back here in a minute. We'll use the rename refactoring to rename this variable so it's correctly changed everywhere it's used. And again, this needs to be an RSocket stock client. We know this isn't going to need a web client because that was only needed for the web client stock client. The test assumes a prices_for method. We want the RSocket functionality to work exactly the same as the web client functionality, so we'll assume our test is correct. Let's create the missing method on RSocket stock client. Of course, the method declaration looks exactly the same as it does in web client stock client, so it feels like a good time to introduce an interface that both clients can implement. We can use IntelliJ IDEA's extract interface feature to create an interface for web client stock client to implement. It seems logical to call this interface stock client, and we want the prices_for method to appear on the interface since this is the method that has the same signature on both client classes. We can get IntelliJ IDEA to replace the use of web client stock client with the stock client interface instead if we want. Let's just go ahead and do the refactor without making any additional changes. Our web client stock client class has been updated to add the override annotation onto the prices_for method and to implement our new stock client. We want to do something similar in RSocket stock client. So let's go to that class and have it implement stock client and add the override annotation to document that this method implements the method on the interface. Now our test is compiling, we can run it to see it fail. It should fail since we haven't implemented the actual functionality yet. Indeed, it fails on the assert not null assertion since we're returning null from the prices_for method. Normally, with test-driven development, we'd take small steps to make the tests pass and have more granular tests. For this lesson, we're going to jump right in and implement the working RSocket client. To make an RSocket connection, we need an RSocket requester. This module doesn't have the correct dependencies yet, so let's go to our pom.xml file. Let's duplicate one of the Spring Boot Starter dependencies and change it to Spring Boot Starter RSocket. IntelliJ IDEA will download the correct dependencies and add them to the module. Back in the RSocket stock client, we can now add the import for RSocket requester. We'll make the field private and add a constructor parameter for it. Now we can use the RSocket requester, giving it a root. In our case, the root is the string value in the message mapping annotation of our RSocket controller method. We also need to send some data to the server. In our case, this is the stock symbol. Then we need to state the type we expect the call to return, which is a flux of stock price objects. We think this method should work, so we'll rerun the test. The test doesn't compile because we added an RSocket requester constructor parameter, and we don't have an instance of RSocket requester in our test. Let's create a method called createRSocketRequester in the test. Let's move it to the top, near where other objects are typically initialized. To create an RSocket requester, we use the builder inside RSocket requester. If we add the auto-wired annotation, Spring will inject an instance of this into our test. To finish up creating our RSocket requester, we're going to connect via TCP to our RSocket server, which is running on localhost at port 7000. We need to call block to wait until we're connected. We're using auto-wired because we want Spring to inject dependencies into the test. To tell Spring to manage the test, we need to annotate it with Spring Boot Test. We expect this to work when we run it, but actually we're missing something important. We get an error that we're missing a Spring Boot configuration, which might be a little puzzling. In fact, this module doesn't have a Spring Boot application at all, because it was designed to be library code shared amongst other application code. It's not an application in its own right. One way to get our test to work in this case is to create a test application in our test directory and annotate this as our Spring Boot application. We don't need to do anything else, and when we rerun our integration test, everything starts up as expected. The test even passes. Since the test passes, we can assume the client successfully connects to the server via RSocket, gets a flux of stock prices, can take the first 5 of these, and checks the first one has the correct symbol. This is a slightly simplistic approach to testing reactive applications. There are other approaches, one of which is to use the step verifier. Using this approach, we can code our expectations for the events that we see. For example, we could take just 2 prices from the flux of stock price and expect that both of these prices have the correct symbol. By calling verify complete, not only do we check these expectations are met, but also that there are no more stock price objects after our expected 2. We can actually replace our original assertions entirely with a step verifier with 5 expectations. This approach can support much more than this simple example, and is also very useful for testing time-based publishers like ours. We have one final piece to consider. Our web client stock client defined a retry backoff strategy and a simple approach for handling errors. We can actually apply exactly the same approach to our RSocket stock client as well. When we rerun the test, we see it all still works as expected. So now we have an RSocket server on the backend emitting stock prices and an RSocket client that can connect to it and see those prices. In the next video, we're going to see how to switch from using the web client stock client to using our new RSocket stock client. Now we have an RSocket client that lets us connect to our RSocket server. We want to use this from our JavaFX application. We intentionally have 2 implementations of our stock client, one for connecting via RSocket and one via web client. Our client configuration only exposes one of these, the web client stock client, as a bean. If we want applications to be able to use the RSocket client, we need to add an RSocket client bean as well. This second bean can also be of type stock client. Let's call the method RSocket stock client to make it clear what we're creating. We'll create a new RSocket stock client and pass in an RSocket requester. We can add this as a parameter for our method. IntelliJ IDEA is telling us that we don't have any beans of this type either. So let's create a bean method that returns an RSocket requester called RSocket requester. Remember from our test that we can use a builder to create the RSocket requester. We'll pass this in as a method parameter. The type is RSocket requester builder like we used in our test. We can use connect TCP and give it localhost and port 7000 because that's where our Spring Boot RSocket server is running. We need to call block to complete this connection. Our stock client project is actually made of 2 modules. This stock client module, which contains the code that connects to the servers, and the stock UI module that contains the JavaFX user interface code. It's the JavaFX chart controller that uses the stock client to connect to the price service and display prices on the chart. IntelliJ IDEA is now giving us a warning in this class that there's more than one bean that matches the stock client type, our RSocket stock client and our web client stock client. We need to figure out a way to specify which client we really want to use. One way to do this is with Spring profiles. We can give each of these beans a different profile. For example, our web client stock client could have a profile of SSE for server sent events. We'll give the RSocket stock client a profile of RSocket. When we go to the chart controller, we can see the error has gone away, but we still need to say which profile we want to use. We can do this by going to application.properties and setting the spring.profiles.active property to whichever profile we want. Let's start with SSE because this should give us the same bean and the same functionality that we had before. When we rerun the application, we can see the application starts up as expected, and the chart shows 2 sets of prices as before. We can also see that the JavaFX application has started up with the SSE profile. If we want to be extra sure that we're using the bean that we think we're using, we could go back to the web client stock client and add some logging. Let's make it clear from the message which client we're using. Now, when we rerun the application, we see that we're definitely using the web client stock client. Let's go to the RSocket stock client and add similar logging so we have the same kind of visibility. Now let's go back to the JavaFX application.properties and change the active profile to RSocket. When we rerun the application, we can see everything still works the way we expect. Only this time we're using the RSocket profile and connecting via the RSocket stock client. So there we have it, a full end-to-end application with a JavaFX line chart that subscribes to a reactive stream of prices from a Kotlin Spring Boot application and can be configured to get those prices either via server-sent events or via the new RSocket protocol. Thanks for watching.